Okay. Good afternoon. I started the video recording. So, how are you? Everything is okay? I hope that everything is clear. Videos should be there. Do you have any question so far? I didn't agree with you any exam date because you are only a few students. So I think basically we can do the exam whenever you want. And I need to talk with Professor Archetti in order to understand when she's willing to make the exam. In principle, we couldn't, I think I already mentioned it to you, we couldn't make any exam before the official end of the lectures, which is the official closure is, I think, June 10, something like that. But given that you are a few students only, I think we could anticipate. I will talk with her. And then your preference would be to take the exam before, as soon as possible, or let's say May. May will be good. May will be good. Also for you and also for you. Also for you, May, the exam in May is okay? In May. May is after April, May before June. Okay, I talked to Professor Archetti and will let you know. Okay, good. Now, let me share the screen. Nobody's attending online, but I want to record also the screen. So we're talking about forcing estimation. And we dealt with, as you may remember, wind forcing, and we got to this relationship here. And now I am also opening the PowerPoint, but before I open it, I wanna, we got to this relationship here, which gives the wind force in kilonewton, depending on several coefficients, and depending on several variables, independent variables that you see there. As I mentioned to you, this is a mixed physically based empirical approach because if you look at the computation of the wind force, it is computed by multiplying the wind pressure, which is given by a diagram here below. So it is the wind pressure multiplied by the surface, the area of the ship that is exposed to the wind. And the pressure is computed by considering a physical law depending on the density of air, specific gravity of air, and depending on the velocity of the wind. So you can recognize a physical basis here. You can recognize a part of a process-based approach. On the other hand, there is a multiplier, CW, which is the wind force coefficient, which makes the overall formulation empirical. Of course, this is a force that is exerted, is made by wind over the ship, and it can be directed in any direction. It can tend to push the ship against the berth, or it can tend to bring the ship outward, seaward. Of course, we have to evaluate the direction of the wind and the resulting forcing in terms of actions over the bollards. So this is why here you see a paragraph on the computation of the wind loads. Let me open the PowerPoint now, because this part here is better if I use a slide. So basically now let's turn, after having computed the overall wind force over the ship, let's try to better understand how this forcing over the ship is transmitted, vehiculated to the bollards. Of course, the ship is moored to several bollards. So this is a bollard, just to give you, this is a bollard. And there are the mooring lines, of course, that transmit the forcing to the bollards. Now let's try to better understand this. So this is the wind force, and remember that this is the sketch that allows you to compute the angle between the direction of the wind and the longitudinal axis of the ship. And you see that there are several mooring lines that generally they are more than the number of 6 that you see here, depending, of course, on the size of the vessel. And I also would like to go back to the web page because I want to give you the names of these mooring lines because they are identified with the proper terms. So let's get the figure here. The number 1 is what is called the headline. It is fixed to the bow of the ship. And the purpose of the headline is to keep the forward part of the ship against the dock. And the number 2 is called the forward breast line. The purpose is to keep the ship close to pier. The number 3 is called the forward spring. It prevents from advancing because, of course, if you look at only at number 1 and number 2, they don't prevent the vessel from advancing. So number 3 has this function. The number 4 is called aft spring and prevents from moving back. Aft is a synonym from stern, what in Italian we call poppa. In English, you can call it aft or stern. Stern is let's say that with aft, you identify the lateral part of the stern. Okay, so basically the stern indicates the overall rear part of the ship. And if you want to indicate the rear side part of the ship, the most appropriate term is aft. But in the current language, in the current speaking, they are synonyms. If you look on the Google Translator, they are synonyms. Aft breast line, number 5, keeps close to pier. And number 6 is the stern line, which prevents a forward movement. So you see that the combination of these mooring lines has been designed in order to avoid all the movements. Of course, you cannot prevent an up and down, but there is to say that these mooring lines are not horizontal. Usually they go from the top of the ship. They are inclined towards the downward direction to the bollards. So there is indeed some action also to prevent the up and down of the ship. Now, how can we estimate then the force that is transmitted through the mooring lines to the bollards 1, 2, 3, 4, 5, 6 in this case? And in some cases, you may have more than 6, more than those that you see here. So, First of all, in order to properly assess the forcings generated by the moored ships, and let me go back to PowerPoint. First of all, let's understand the type of movements that the ship can be subjected to. So the ship may be subjected to translation and rotation. And these two movements, translation and rotation, can take place along 3 axes: the longitudinal axis, the transversal axis, and the vertical axis. So if I look at the ship, this is the longitudinal axis. Longitudinal. And then perpendicular to the longitudinal axis, you have the transversal axis. And then you have the vertical axis, which is in the vertical direction perpendicular to the ship deck. So you have three axes. This one is the vertical axis. Of course, this is displaced on an horizontal plane, so the vertical axis is represented just through a point. Okay, and then you can have along these three axes rotation and translation. So you have six movements, which corresponds to the 6 degrees of freedom. Okay. The ship is a rigid body, so it has 6 degrees of freedom, which correspond to the 6 type of movements. In general, you may have all of these movements together. When we talk about wind forces, generally we don't consider translation along the vertical axis. We may consider rotation along the vertical axis, but we don't consider translation. Usually when we talk about wind forces, translation along the vertical axis is considered when you talk about the forcing exerted given by waves, because they generate an up and down. Okay. So now the question is how we can decompose these forces along the mooring lines and the forces given by these possible movements along the mooring lines and along the over the bollards. First, let's consider that when we talk about wind forces, let's talk only about, as I said, movements on the horizontal plane. And what we need to compute is, first of all, we need to, sorry, this is still the previous slide. Okay. The components of the horizontal forcing, of the wind forcing, along the 2 directions of the transversal axis and longitudinal axis. Okay, so let me go back to the web page because it's more detailed. 1 second. It's here. Perfect. Here we are. So if the wind blows at an angle to the ship, we have 2 components, and these components, let's call them FDX, which is along the direction of the berth structure, which means that it's the longitudinal axis. And this is given by the component along X of W divided by the length of, because this is a distributed load, sorry, I forgot to say this. This is the computation of the distributed load along the berth structure. So let's suppose that is distributed, okay? So the distributed load is given by the component of the load in the considered direction divided by the length of the berth structure. And this allows you to compute the distributed load against the body of the berth. Of course, then you have to verify the berth in correspondence of the bollard point. And for doing that, you need the computation of the single forcings over the bollards. For the computation of the distributed load, you just need the knowledge. You just need to compute the component that is given in the X direction and divide it by the length of the berth. Okay, this forcing can be distributed in both directions. So basically, you can compute a force. This is the berth. Okay, and let's suppose that you have a vessel here. Okay, you can have a forcing given by the fact that the ship is subjected to forcing in this direction, and this is F, let's call it F distributed Y, which is given by the component of the wind direction along the Y direction divided by LQ. Okay, this is LQ. And this is something that basically you can schematize it in this way. It's a forcing distributed over the body of the berth pointing seaward. Okay, and then you may have a forcing Fdx, which gives, in a distributed manner over the berth, a forcing in the other direction. So it is something that you can schematize in this way. Again, this forcing distributed allows you to size the overall body of the berth. And then you need to compute the single forcing along the mooring line. Let me choose another one. So let's suppose that you have a mooring line here. Oh, it's again black, sorry. And this is a bollard. Okay, this is a bollard. You need to compute the single action over this bollard in order to check the anchorage of the bollard to the body of the berth. So the body of the berth should be sized in order to resist to the overall forcing. And the single bollards, of course, the anchorage of the single bollards must be sized in order to put a reinforcing around the bollard in the body of the berth. Okay? So the computation of the distributed load is quite simple. As you can see over the screen, you just have to decompose the wind forcing in the two directions and divide by the length of the berth. And then we will talk about the computation of the forcing along the single mooring lines. Okay. Okay. Now, in order to compute the forcing along the single mooring lines, we need to take into account the rotation of the vessel. Before talking of this, let me define the terminology of these 6 movements that I just mentioned. Okay, let me just find it. I think it is down there. Because I think that you can see here a sketch of the ship with the 6 degrees of freedom. Okay, X is longitudinal, like in the scheme that I depicted on the blackboard. Y is transversal and Z is vertical. Good. Now, the 6 movements. I think this sketch here is nice and it's clear. So when we talk about rotation, the rotation along the transversal axis is called pitch. The rotation along the longitudinal axis is called roll. And the rotation around the vertical axis is called yaw. So yaw, pitch, roll. So if you want to start from the longitudinal axis, it's rotation around the longitudinal axis is roll, rotation around the transversal axis is pitch, rotation around the vertical axis is yaw. Translations. Let's start again from the translation along the longitudinal axis. It's called surge. The translation along the transversal axis is called sway. The translation along the vertical axis is called heave. Okay, so surge, sway, heave. And respectively for rotation, roll, pitch, yaw. When we talk of wind forcing, we forget about the heave, and we forget about the pitch, and we forget about the roll, and we consider the yaw. We consider the rotation around the vertical axis. And we also consider the sway and the surge in terms of translations. So only one rotation, only one rotational moment along the vertical axis, and then two translations along the longitudinal and transversal axis. Now we have to better understand rotation, how rotation takes place. So when a ship is exposed to wind, how does rotation takes place? You understand that rotation is originated if the wind, in a way, is asymmetric with respect to the ship, asymmetric in some way. If you get a wind that is causing a rotation, you understand that there must be a mismatch between the center of gravity of the wind pressure and a kind of center of gravity of the ship. I say a kind because it is not really the center of gravity of the ship, the point that I am interested in. So what is the point I am interested in? Let me just use the blackboard again. And let me now represent a ship on the vertical plane, not on the horizontal plane. So here is our ship. Okay. With some here is our ship, and let me draw. I don't think I have a blue marker. Okay, so let me draw a waterline here. Okay, so this is the submerged part. So you have a wind edge area, which yeah, because this is the blue cap, but it's still black. This is the wind edge area. Let me mark it. Okay, so the area of the ship that is exposed to wind. And this is the area where I get the wind pressure. And this wind pressure, it's may have two components. Let's assume now that the wind is perpendicular to the side of the ship, which is not a limiting assumption. Even if the wind is not perpendicular, you can compute a component that is perpendicular. Okay, so given that here I'm talking about the side component of the wind action, let's suppose it's the direction of the wind is perpendicular. So the wind is pushing, and what is the point of application of the wind forcing? The point of application, the point where the resulting wind force is applied, is the center of gravity of the area of the wind edge area. So this is center of gravity of the wind edge area. Of wind edge area. Okay, so this is quite clear and quite simple. Okay. Now, when there is rotation when the center of gravity of the wind edge area is shifted with respect to what? With respect to the point where the ship stands to rotate around. So let's suppose that you have a ship that is rotating, okay? If it is rotating around a point or around the vertical axis passing from a point, okay? So if I have rotation may occur, for instance, around this vertical axis. this vertical axis is passing from a point which is called the pivot point. This vertical axis of rotation is defined as the vertical axis such that if I stand there, so if I stand over the pivot point, I perceive while the ship rotates, I perceive a rotation, but with just around myself. Okay? It's a vertical axis, the ship is rotating around. If there is a forcing that tends to cause rotation. And where is located this pivot point? Where is the location of this vertical axis of ship rotation? It is located, the pivot point is the center of gravity of the underwater part of the ship. Of underwater part. So, what is the moral of the story? The moral of the story is that if the center of gravity of the windage area is shifted with respect to the center of gravity of the underwater part of the ship, you get rotation.
Shift, you mean it is not aligned?
Yeah, I mean that there is an eccentricity between the two vertical directions here. Okay, you have here, this is a shift. If you get the wind that is pushing with the resulting forcing just against the pivot point or any other point located along the vertical axis passing from the pivot point, you don't get rotation. You just get translation. You just get the movement that we called here sway. You have sway, but you don't have yaw. But what often happens is that these two centers of gravity are not aligned. Also keep in mind that the pivot point is moving. It is located in the center of gravity if the ship is not moving, if the ship is standing, okay? Because you understand that if the ship moves, then the rotation is the position of the vertical axis of rotation changes. So, if the ship is standing and you have the wind, once again, that is resulting in a force that is aligned with the vertical axis through the pivot point, you don't have rotation. If there is a shift, an eccentricity, you get rotation. So basically, what is important for us is to estimate, for sure, the resulting force over the side area, the resulting from wind. So what was called before, I think we called it Fy. So the component of the wind forcing over the side area of the ship. And then we need to compute the position of the center of gravity of the windage area and the position of the pivot point. The position of the pivot point for a standing ship, of course, it may also depend on the load of the ship, because if you get an increase of the underwater part of the ship, you may have a slight change of position of the pivot point. Actually, usually the pivot point in standing condition is given as a fixed position, because the change that you get usually, because the water line level changes, are minimal. But when the ship moves, you may have a relevant change of position of the pivot point. You understand that the pivot point, more or less, very roughly speaking, it's located midway between the stern and the bow, more or less. Okay? It's not precisely midway, but it's more or less midway. When the ship is moving forward, the pivot point moves forward as well. And it moves forward by reaching about halfway between the original position and the bow. And we say that the position of the pivot point is located at about 1/4 distance from the bow of the overall length between perpendiculars. So 1/4 of the ship length measured from the bow. So it's about midway between half bow, half ship, and the bow. And the same if the ship moves backward, we have a shift of the pivot point in the rear part of the ship. But we are interested in the berthed conditions. I just wanted to mention to you that the position of the pivot point depends on the movement of the ship, but we are interested in the berthed conditions. So let's just focus on this definition. Okay. Now, let me go back here. I wanted to anticipate this terminology, but let's go back here now to wind forces. So we need to assess then the drift and the rotational moment. And then once that we have computed the rotational moment and the two components of the wind forces, then we need to work on the position of the mooring lines and estimate the forcing along each of them. Okay, and so this is the subject of an exercise which is here. 1 second, I open another page, which we will make together, and we will start today, but later. Okay, so if you go to Harbour Engineering here, you get an exercise here, computation of wind actions on a moored ship and computation of mooring forcings. And here you see that there is a sketch. The exercise gives the coordinates of the bollards and the chocks. The chocks are, 1 second, I show to you. I'm not sure if I already show you what are the chocks. And let me see if let me see if I can get an image already. Yeah, you see, it is this one, the chock. It is, the mooring line is binded to an anchorage over the ship, and then the mooring line passes through the body of the ship by the chocks. Okay. And here you see other images. You see, this is the chock. So in the exercise, you have the position of the chocks here, C1, C2, C3, C4, and you see that there are the coordinates here and the coordinates of the mooring lines, because what matters for the computation of the bollard forces is the position of the chocks, not the position of the anchorage in the ship. What matters, besides the position of the chock, is the overall length of the mooring lines. And you see here, mooring lines are 15% longer from bitts to bollards. Bitts is the name of the anchorage. I didn't remember, sorry, over the ship. They are called bitts, okay? And it is specified that the mooring lines are longer, 15% longer from bitts to bollards than the distance between bollard and chocks. Why this is specified here? Because in order to estimate the bollard forces, you also need to know the total length of the mooring line. Why? Because there is elasticity. There is elasticity. Here it is assumed that the wind blows perpendicularly to the longitudinal axis along the transversal axis. To simplify things, but in case you have a component along the longitudinal axis, you have to compute the wind force along the transverse direction with a simple decomposition of forces, and then you have also to apply the resulting forcing on the longitudinal axis. Here it is assumed that you have only wind blowing along the transversal axis. So the wind computation is relatively easy. We have to apply the formula that we studied last week, and it is relatively easy. And then it is given the position of the pivot point. You see here PP, this is the pivot point. It is given the position, and somewhere here there is written here, by assuming that the origin of axis is placed over the pivot point, and I think it is given, let's read it later, but it is given the position of the position of the point of application of the resulting wind forcing and the position of the pivot point. Now, from the point of view of structural mechanics, here the problem is that you have a force and a rotational moment acting on a rigid body. The rigid body is binded to the bollards through elastic lines. It's a matter of force decomposition here. Basically, you have to decompose the forcing and the rotational moment to find each individual forcing along the mooring lines, which mooring lines are elastic. So it is a problem of structural mechanics. I will give you the relationships, because the relationships, there is a method for computing, for decomposing forces and moments along elastic lines, which is codified in structural mechanics. I will give you the means, the formulas for computing the mooring lines. We are not refreshing the theory, because this is related to the theory of elastic bodies. You know, it's a bit complicated. You know that structural mechanics is a bit complicated, so we don't refresh the theory. I give you the resulting relationships, and you will see that it is a bit complicated, but actually, once that you know the relationship, it's just a matter of applying them. So we are not refreshing the theory, as I said, but on the other hand, I think it is instructive to compute, to solve this exercise. We will do this later today, okay? After the break, we will concentrate on this. Good. Now, let me go back here. So basically, with wind forces, we are done. What did we do? We discussed the relationship to estimate wind forcing over a moored ship. We discussed the need or not to decompose the forcing along two directions. And you have this need if the wind is blowing midway between the two directions. And we discussed the fact that we get, as a result, a wind drift and a rotational moment. And the rotational moment originating yaw. And we said that the rotational moment depends on the position of this pivot point, which basically shows you where is the vertical axis of rotation. And then we discussed the terminology to indicate, to identify these 6 possible movements of the ship. Okay, and then finally we discussed how to compute, basing on the resulting wind forcing, the distributed load along the berth, here, and the concentrated load over the bollards. And we will make an exercise. We emphasize that this concentrated load depends on the position of the mooring lines, of course, and mooring lines that are elastic. So this is a problem of structural mechanics. This is where we got. We don't give more details. Now, you may ask me, what do we need to remember for the exam? First of all, for your background, your skills, try to have clear the overview of the problem. And if it is not clear, please let me know, okay? And for the exam, I already mentioned to you that please remember this relationship here and be able to explain the meaning of each of these variables, independent variables and coefficients. And then please make an effort to remember the terminology of these 6 possible movements. It is also a problem for me every year. I have to refresh because it's something that it's unusual. They are unusual terms, but please try to make an effort because they are frequently used. And I think, remember, of course, the definition of what is a pivot point, okay, and where it is located. And I think that's it. You don't need to remember this terminology for the mooring lines. Do you have any question? Okay, now we should talk about wave forces and current forces. Wave forces are originated by the fact that you get waves that basically cause a movement of the moored ship. Waves are not really as severe as in the open sea because harbors are located, ports are located in a sheltered area. And therefore you have to expect waves that are a bit mitigated in terms of wavelength and in terms of wave height, especially amplitude. But still, you understand that even in harbors, and you can see it if you visit an harbor, we may have some movement of waves, which are, by the way, also reflected by the piers if they are not open. And therefore, we have to take into account this wave forcing. And we may also have currents originated by, for instance, inflowing rivers or tides or thermal differences between the open sea and the harbor. And the difference between wave and currents, I think you know it. And waves are basically given by a shift of energy up and down with no mass movement unless you get a breaking of the waves. Currents are given by a shift of both mass and energy. Because with currents, you have indeed a volume of water that is moving. And typically it is moving without oscillations or with very long wavelengths of the oscillation. But it is a movement of mass. Waves are, in general, a movement of energy. The movement of mass is very limited, and unless they break. If they break, of course, you translate part of the movement of energy into movement of mass. But before getting into wave forcing, you may remember that we skipped the probability. You know, I could skip probability because we didn't talk about estimation of wind velocity, which is a random process. It's wind is considered to be, of course, it's physically based, but usually we describe it by using random processes because we cannot describe wind in a deterministic way. And the same is true for waves. So it is true that also for wind, we have to estimate this extreme wind velocity. And usually we do that with the theory of probability. You may remember the windrows. The windrows is about frequency, and frequency is about probability. But when we come to waves, indeed, it is really the place where probability theory comes into play. And therefore, before getting into wave forcing, I think we need to refresh a little bit what we mean by probability. I should have done it before, but I didn't want to make it last time. Now it's time that we focus on probability. And of course, we need to be very quick on that. I think for sure, you had already some background of probability theory. I am also sure that probably you forgot part of it because probability theory is not easy to remember. It's something that looks also a bit nasty. And as I said, it's not easy anyway to remember it. So I don't think that you are really very strong in probability, based on my experience. But on the other hand, I know that you had some background. So I try to be quick and I try to be very technical, but I think that we really need to fix in mind some basic concepts, some basic ideas. Because when we talk about wave estimation, we talk about return period. And I'm sure that you already heard this term, like I need a wave with the 100-year return period. You understand the meaning, what it means, even if you don't have any idea of return period in terms of statistics, but you understand what it means. A wave with the 100-year return period. It's a wave that we observe more or less every 100 years. And the legislation tells you precisely this. So you have to estimate, you have to size the births, the ports for a return period of X years. So we need to understand what it means. Return period is nothing else than probability. And probability, by the way, is not much different with respect to frequency. And you understand why. In frequency, probability, it's more or less the same meaning. So let's try to refresh a little bit some basic concepts and some understanding of probability. And you have a box here. Okay, don't be concerned because I make it very, very entertaining. So first of all, I have also a R window open here because I want to make this, let me clear the screen. I want to make this very, very, as I said, entertaining. So one thing that I did is, one thing that I already mentioned to you is that probability is a synonym to frequency. Actually, it's not really a synonym. It's not really a synonym. So let's think of the experiment of tossing a coin. Tossing a coin, what is the probability of getting an head? What would you say? If you are asked, what is the probability of getting an head from tossing a coin? What would you say? 50%, okay, correct, 50%. It's or 0.5. It's the same thing. And did you get this feeling that it's 50%? By? Between the error case and all the possible cases. Okay, this is a good, yeah, this is a good point. This is a good point. So it's really an estimate of probability. Yeah. There are other two ways which you could get this intuition. So what you defined is the precise definition of probability for a discrete event, for a discrete variable. So let's say tossing a coin is like you can associate to the head the 0 and to the tail 1. So it's a binary variable. Now, there are two other ways to get this intuition. The first one is precisely by intuition. You understand that if I toss a coin, it's I exclude the possible outcome of the coin standing up on the edge. And then I say, okay, for sure, I have it's 50% because it's impossible that I have a probability more than 50%. This is another way by intuition. And in this case, you don't really see the difference. But I give you another example. If you are asked, for instance, what is the probability of a candidate to a position, like a candidate for the position of the major. There are two candidates, so similar to tossing a coin, but you understand that you can't say the probability is 50% of each of them, because you may have some additional information that brings you to say, I think candidate A has a probability of 70%, and this is by intuition. And the same can be applied for the coin. And this way of intuitively estimating probability is called Bayesian. Okay, you use your prior knowledge to assign a probability. Okay, good. And finally, there is another way to estimate probability by experiment. And let me do it in R. So in R, I can generate random numbers and by a function that is called RUnif. And it means that random numbers, and I want 10 of them in the interval 0, 1. Okay. And you see here the random numbers. Okay. And now, given that I want a binary variable, let me see if I can round it, round these variables, and see whether or not I get a vector of 0 and 1. Yes, you see. Perfect. Now, this is like tossing a coin. I can do it like 5 times. It's like tossing a coin, okay? And now, how can I compute? This is like making an experiment. I toss the coin several times, and I compute the outcome by simply dividing the number of heads by the number of trials. Like here, for instance, I generated, let's say that head is 0 and tail is 1. I generated 5 random numbers, 0 and 1. And if I want to estimate the probability based on this experiment, without knowing that it's tossing a coin, without knowing that it's a random number generation, I would say, okay, the probability of getting 0 is 3 over 5. It's basically what I can do is making a sum of these points, and I can divide by 5. This is the probability of tail, actually. It's 0.4 because it's 2 over 5. Okay? So this is the probability, again, of getting 1. Now, you see that the result is a frequency. What I computed is a frequency, is the frequency of tails, the frequency of number 1. The result is not 0.5. I was expecting 0.5. So this highlights a limitation of what I said. Frequency is not probability. Probability is 0.5. Here, frequency is 0.4. Now, if I increase to 10, and then I divide by 10 here, now I get to 0.5. If I make another attempt, it's not really 0.5. Another one, you see that, and in this case, even with 10 numbers, I got 0.2, which means only 2 ones and 8 zeros. So the frequency is not really a probability, because if frequency was a probability, I should get every time 0.5. But let me clear the screen. If I increase to 1 million, 3, 6, and here 1 million, very close to 0.5, very close to 0.5, very close to 0.5, very close to 0.5. You see? So frequency is asymptotically identical to probability. Asymptotically. You make a number of attempts that is very large, and frequency is equal to probability. So this gives us a way for computing probability of whatever we want to compute by measuring the frequency, provided we have a long observation record. This is why when you design, you make a design project, very often people say you need a long observation record. Why? For this very reason, because actually you need probability. In engineering, almost any design is based on probability. And we assimilate it through frequency. And this is basically the demonstration that computational probability is very simple, provided you have a long record. If we had a very long record, we didn't need any theorem of statistics or probability or whatever. With a long record, we could make the design by just computing frequency. but we don't have a long record. And keep in mind that sometimes, very often, it may happen that you have to make a design project without any observation of waves. We are talking about waves here, okay? Without any observation. So if you are in such a condition, keep in mind that when you are without data, you can get a lot of information even from a short record. So the first thing that you have to do, given that measuring waves is relatively easy, the first thing that you have to do, if you get a task to make a project of an Harbour with no data, put a monitoring system in place, because even with 1 year, you can get significant information. Of course, waves are seasonal, so you need at least 1 year, or at least 1 year of the storm season. So one storm season. Okay. So this is how we estimate probability, and the same for rolling a dice. For rolling a dice, it's same thing. And let me go to RUnif again without the sum. Okay, so here it would be 1, 6. Let me see what is, yeah, this is like rolling a dice. I think so. I'm not really sure if I could, yeah, I think so. Let me just see with 20. I never get 1, so I think that round is, I'm not sure it is, I think what I should do here is floor, because round, I think rounds to the nearest integer. So floor between 1 and 7, I think this is like rolling a dice. 1, 2, 3, 4, 5, 6, 7. I think so. Anyway, let's, because these are like games, I don't want to insist on this. The only thing, keep in mind, is that, so let's define then probability in a formal way, okay? Because I was saying the only thing is that here, for the dice and the tossing a coin, we are dealing with integer variables. So keep in mind already from now, when you go to continuous variables, there is a complication. Because continuous variables, you understand that you cannot compute the frequency, because a continuous variable has like an infinite number of digits. So you will never get from a continuous variable the precise value that you want. So for instance, if I stimulate continuous variables, you see here you have a number of digits that is limited to 6. But in any case, if I say I want to compute the probability of getting 6.000000, you will never get it. So when you deal with continuous variables, there is a complication. But now let's stick on the case of discrete variables, which is easier to understand. Okay, and let's define then what is probability. First of all, we understood it's like a frequency. But actually, we can say that to estimate probability, we can use the frequency, but it's not a definition. It's not really a definition. And the definition of probability is something that measures the likelihood of an event. But this is still not a formal definition. So statisticians in some time ago struggled to find a definition of probability, a mathematical definition. And Kolmogorov solved the problem by defining 3 axioms that define probability. And of course, these are very general. And you have to make sure that the way you then estimate probability complies with these 3 actions. And they are quite simple. So First of all, axiom 1, the probability of an event is a real number greater than or equal to 0. This is not an O, is a 0. Sorry, I see now, just now, the mistake. Axiom 2, so greater or equal to 0. Axiom 2, the probability that at least one of all the possible outcomes of a process, such as rolling a die, will occur is 1. I try to explain better. The space, how you defined it before, includes all the possible outcomes. So the probability of getting at least one of all the possible outcomes is certainty, okay? And it's 1. So basically, if you bridge axiom 1 and axiom 2, you get that probability varies from 0 to 1. Axiom 3, if two events A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A, sorry, not A, plus the probability of B. So let's refer again to tossing a coin. The two events, head and tail, are mutually exclusive. If I get a head, I don't get a tail. And then the probability of getting either head or tail is given by probability of head plus probability of tail. Okay, this looks like very trivial to you, but please remember the axioms. You can get this question. Remember the axioms because they are the agreed way to define probability. And a consequence of these three axioms is that the probability of the impossible event is 0, and the probability of the certain event is 1. Okay? It's a logical consequence of these axioms. The axioms have been devised in order to comply with different way of estimating probability and to comply with some other deductions that can be derived, like probability of the impossible event is 0. Now, you have to make sure that whatever you estimate probability, you comply with these axioms. So basing on frequency, you comply with it. And if you prefer to estimate probability by intuition, then you have to make sure that your estimates comply with these actions. And to make a trivial example, two candidates for an election, you cannot say that both of them have 60% of probability to win. If you say that the first one has 60%, then the second, as a logical consequence, has a probability of 40%. And this is what you have to say. Of course, sometimes when we talk about probability, we can talk in terms of percentages or in terms of fraction of the number 1. Okay. Okay. Now, probability distribution. A probability distribution assigns a probability to a considered random event. So, for instance, let me make the example again, of tossing a coin. The probability distribution is very simple. Probability distribution, if you indicate the symbol x in the random variable, the probability distribution is a function px, which gives it's a function of x, which gives to you the probability that you assign to each outcome. So it can be defined with simple assignments, like for the case of tossing a coin, P0 equal 0.5, P1 equal 0.5. Okay, this is already your fx. Sorry, I used a different symbol for f. Let me use the same one. So it can be defined by point, or you may have, and this is a discrete function, okay, because it's a discrete random variable, it's a discrete function. So this is a probability distribution. So when you get this term, you listen of a probability distribution. It's very simple. You have to identify all the possible outcomes and then assign a function. For tossing a dice, you may write that P1, or let's say Px, is equal 1/6 for each x, where x is given by 1, 2, 3, 4, 5, 6. Okay. So the probability distribution then can be estimated, look there, with the frequentist approach. So don't look there because this is already the next step. With the frequentist approach in this case, so I estimate the number of 0 and then I divide the number of 0 by the total number of attempts. And that's it. Now, let me introduce the complication of the continuous variable, because as I said, you cannot apply the same procedure. You cannot estimate the probability of 6.00000 by counting the number of outcomes. So what we do in this case, the idea is to make the continuous variable discrete. So I have a continuous variable and I try to split it in discrete intervals. So if I have a continuous variable x here, from 0 to infinity, or let's say from minus infinity to infinity. It's a generic example. The idea may be that if you want to identify the probability of a specific value x star, what could be the idea? The idea is, okay, I cannot get the precise value of x star, but I can count in a way, I mean, I can look at the number of points that get around to x star. And this, from a technical point of view, is also very reasonable because I'm not interested in the 10th digit. So what I could do is, let me just look at how many points I collect around an interval around x star. So basically, what you could do is for instance, let's go again into R. So the function RUnif generates random numbers, okay? And you give the number and give the range, 0, 1. And they are randomly distributed, okay? If you make a plot RUnif, let's say 100, 0, 1, you see they are really randomly distributed. And this is the variable on the vertical axis. You don't see really some regular pattern. Now, let me make another thing, sorry. Okay, let me use another function. This function here generates numbers not from a uniform distribution, but from a normal distribution, Gaussian. And if you don't know what is a Gaussian distribution, just keep into account that, consider for now that it's not randomly distributed in the range. And I need to give two parameters, 0, which is the average, and standard deviation, which is 1. And let's see the plot. Now, what can you see here? You see that it's not like before, okay? And I give to you again. You see, this is the first plot, and this is the second. There is a difference. Here you see that there is, the points are concentrated around zero. There is a greater density of points around zero. So if I see that there are a lot of points here, a lot, okay, and less here and there, what I see is a higher density of points for some values. So the idea may be that of computing this density. So let me fix the interval around x. Okay, so this is x star, and this is x star minus delta x here, and this is x star plus delta x here. And then let me compute the frequency of the points that are inside this interval. And let me go back to the web page because I need the formula. It's yeah, sorry, it's here. Okay. So the frequency is computed. Look at the above formulation. Frequency of x minus delta x, x plus delta x, is equal to the number of points that I get into this interval divided by the total number of experiments. So I computed the frequency of the points that fall within this interval. Just notice that here I indicated the variable with x star, the precise value of the variable I'm interested in, and there it's x, but it doesn't make any difference, okay? So I compute the frequency of the points inside this interval. And this is an indication of probability. It's clear. It's an indication, it's a measure. It's in some way connected to the probability of x star. On the other hand, that value, frequency, depends on the size of the interval, depends on delta x, which is not reasonable because the probability of x star, it's a number that cannot depend on an arbitrary decision of width of the interval. So what is the idea here? Is that, yeah, I have to get rid of this subjectivity. And therefore, the idea is, look at the second equation here. Let me divide the frequency by the length of the interval, by 2 delta x. And in doing that, I divide the frequency, and the frequency, remember, it's like probability, by an interval of the variable. What I get is not a probability, is a density of probability. Is the density of the probability inside this interval. Density. And this is why we call this probability density, not probability. So when we deal with continuous variable, we need to resort to an additional definition of probability, which is the probability density in additional form. And then if we compute the limit of the density which I have computed for delta x that tend to 0, because you understand, it becomes, I need a measure that is the closest possible to x star. So I need to make the width of this interval very, very small. And then I need, because we already know this, that the number of attempts tends to infinity. This is an estimate of the probability density. Is this clear? This is the idea, okay? And the original idea was just to count the number of outcomes that are interesting to me, like that. It is very simple. Here, I cannot count the number of outcomes because it would be 0, the outcomes of x star. I define a density. And you may say, yeah, but this is not probability. So is it useful anyway? I anticipate. Yes, it is useful. But before we move forward, let's make an example then. Okay. So into R, I just have drawn this graph, and can we compute the probability density in practice? Yes, we can. We just have to define, if we want to make the computation, a value of delta x. We need to define it. And you understand that if you have few numbers, delta x cannot be very small, because you may get some discontinuity and some part of the interval where you don't have any outcome. So delta x must be something not very small if you have just a few numbers like here. So now let's compute the density. So first of all, let me give no, we can do it directly without defining a variable. So what I need to do is start from the generation of numbers, and let me split. It's a variable that is defined between minus infinity and infinity. So I think what we do, it is defined between minus infinity and infinity, but let me just look at the plot again. You see that the values are between, no, this is uniform, sorry. The values are between -2 and -2 and 3. Let me make an adjust because I need to be a bit empirical. -2 and 2. Okay, let's draw the density between -4 and 4. Okay. So this is the variable, and what I need to do is okay, let me define a variable a equal to, okay, and then I have to count, I have to split the interval between -4 and 4 in subintervals, and I need to count in each subinterval how many outcomes of A are included. So let's split this interval in chunks of 4.5, -4, 4, -3.5, -3, -2.5, etc. Okay. So what I need to do is there is a way to compute the outcomes from a vector that are included in some subintervals, which is estimate using the function length of A. If I just write length of A is 100, length of A, and here I can put a condition like A greater than 0. You see? I can put conditions, length of the vector A greater than 0. Now, let me just see how I can put two conditions, A less than 1. Let's see if it works. No, just 1 second. Okay, good. We are done. Now, let's, what we need to do is we generated this A, length A greater than -4, and A less than -3.5. Minus. This should work. Sorry. Yeah, okay. Let's try to do that. 0. Okay, I have 0 between these two, and if I here make -3.5 -3, it's 0 again. I'm not sure. Let's see, minus 3 minus 2.5. It's 1, okay. And then minus 2.5 minus 2, 2 minus, sorry, yeah, minus 2 minus 1.5. You see, I am computing these numbers. Okay, now, in order to make the computation in only one solution, let me clear the screen and let's make a 4 cycle. 4 I in 1. This is also a way, if you don't know how to make cycles into R, this is a way to learn it, okay? And so it's the interval is 8. So let's limit our interval. Okay, minus 4, 4, it's 8 divided by 16. 1/16. I think this is 16 intervals, yes. Now, the 4 cycle must be followed by the instructions that you want to repeat each time. And if they are more than 1, you have to put a curly bracket. And let me just see how to get the curly bracket from this keyboard. 1 second, Shift A. Okay, I did Shift Alt GR and square bracket, and I got the curly bracket. Now, all the instructions that are included in the curly brackets are executed each round of the cycle. Okay, what I need to do now is to get back the length. However, I need to make the interval varying depending on the variable of the cycle. So varying on A, varying based on I. So I would say that, let me delete this, greater than, A greater than, okay, for A equal 1, it should be minus 4 plus I minus 1 times 0.5. I think this should work. So for in the first round, AI is equal to 1. So at the first round, the result of this computation, this one, at the first round is just minus 4 plus I is 1, minus 1 is 0, minus 4. The second round, I is equal to 2, so it's minus 4 plus 1 times 0.5 is minus 3.5. Okay, good. And here I have to put minus 4 plus I times 0.5. I think that's it. And then it should be okay. Let me see. Yeah, it should be okay. Now let me put here cut, which means print over screen. Cut, length, okay. I had to define the variable because, okay, let me just do this. Let me repeat the computation for curly bracket, okay. Here I put B equal, good, and then cut B fill equal true. Fill equal true means that new line, okay. And I think now we can close the curly bracket. Okay, let's see if I made some mistake. Okay, these are the counts. 0, 0, 1, 2, 2, 10, 16, 14, 22, 13. Okay. Now, let me assign this count on a vector because I want to plot it. So I repeat the computation. You can see it. Okay. So I go back with the arrow up for I in 1 to 16. Okay. And let me just write here B1. So let's assign it to a vector. And then I can avoid cut and I just make, okay. I think it gives to me a mistake because B is not defined. Let's see. Oh, no, it's okay. Okay, so let's repeat it because I made another mistake. BI. And then I can close it. Okay, now we can do plot B. And let's put the lines. Type equal line. So this is my density. Actually, it's not a density because I computed only the number of counts, the number of outcomes. So it is proportional to the density. In order to find the density, if you look at the formula, I have to compute the frequency of the counts. So frequency means that I should divide these numbers that I got by the length of the interval, which is, by the way, it's 0.5. And this would be the frequency, okay? And then I have to compute, I have to divide by the total number of outcomes, okay? So if I wanted to get the frequency, what I should do, if I want to get the probability density, an estimate of the probability density, what I should do is, let me repeat it. Okay, BI, I should divide it by the number of trials, which is, I think, 100, and divide it by 0.5. I think it should work. Okay, I don't need the curly brackets because it's only one instruction. Let me try to plot it. Or let me make one thing. Sum B is 2. So there is something wrong here. Because the way I defined it, first of all, let me check the length of A. Yeah, 100. The way I defined it, it should be the sum of these counts should be equal to 1. Let me just check. It's yeah, it's 100. This is correct. And yeah, I should divide by times. Just 1 second, because it's 4 minus 3.5. So the width is indeed okay. Let me forget about it and let me plot it. Okay. I will find the mistake. There is something that is wrong in the computation. Okay, this is the plot. So let's suppose that this is my density computed. Okay. Let's suppose that this is my density. Now, I said just a few minutes ago, this is anyway useful, even if it's a probability density, because you can derive the probability of the number by using the density. So let me just, on the blackboard here, what is my problem? My problem is to estimate the probability that a wave exceeds a given value. So if I put the wave height over here, wave height, for instance, and it is limited by 0, I want to estimate the probability that the wave height is exceeding 4. Okay. Why? Because I need to design, to size my harbor, my berths, basing on the occurrence of a wave of 4 meters. And I want to estimate the probability of getting the wave of 4 meters, because if this probability is very low, I am fine. If I see that the probability is indeed large, then I am not fine. Okay, so this is my design variable. This is my design variable. Usually the problem is the opposite. I am given the probability and I need to estimate the wave height. But in this case, my problem in any case is to estimate the probability of 4, not precisely the probability of the wave to be precisely 4, but the probability of the wave exceeding 4, okay? Which is the same thing as the wave not exceeding 4, because we know that the probability of the whole space is 1, so the probability of wave greater than 4 is equal to 1 minus the probability of wave lower than 4. Okay, lower or equal. So you can talk of probability of exceedance or probability of not exceedance, and you can get the other, the one by the other, because the sum of them gives 1. Okay, so how can I estimate the probability of, let's say, not exceedance? I prefer to talk about the probability of not exceedance because usually this is the probability that is estimated. And then if you're interested in the probability of exceedance, you just compute the complement to 1. Now, let's suppose that I know the probability density for each interval. The probability density for each interval, in order to get the probability of not exceedance, so let's call it with capital B of 4, is given by the integral of the density, integral between 0 and 4 of the lowercase p. Let me indicate with the lowercase p the density of, let me call it x in the x. So if I compute the integral of the density, I get the probability of not exceedance. And if you look at the definition of the density, you understand it. Because you see how it is computed. It is the number of the frequency of the outcomes within each subinterval in its infinitesimal delta x divided by delta x. If you basically integrate over delta x, you get the sum of the frequencies, which gives to you the probability. The sum of the frequencies is the probability, the sum of the probabilities of getting anything between. And by the way, in making this computational derivation, I understood that my calculus was correct. Because the sum was 2, but the length of the this integral basically I discuss later. Okay, after the break. In any case, what is the moral of the story here? Continuous variable. I need to define a probability density. The way I defined it, it's there. Why it is useful? It is useful because if I integrate the probability density over an interval, I get the probability that the variables falls into that interval. So if I integrate the probability density over the interval 0, 4, I get the probability of getting something here. So if the computation that I made is correct, if I compute this integral over the total range, I should find 1. Okay. So I repeat, if my computation was correct, my computation is here of densities. If I compute this integral between -4 and 4, I should find 1. Because it's the probability of getting the variable within the whole range, it's 1. Okay. Good. Actually, in order to, okay, I'll do it later. In order to make the computation, it's better if I put on the horizontal axis in this graph the variable. Because I have the density on the vertical axis, I should put the variable in the horizontal axis. And the variable is from -4 to 4. Any question before we make a break? I'm already a bit late. Okay. Thank you. See you in 15 minutes. Okay. Okay, so let's try to make a summary of what we did. Basically, I think everything is clear for the discrete variables. For the continuous variables, I said, let's compute the frequency in this way. Suppose that we make a total number, capital N of experiments, generation of random variables, and we split the interval of interest into several subintervals. And we compute for each of them the number of variables that fall into the interval and the frequency. The frequency is computed by the number N1 divided by N. Okay? And then, in order to estimate the density of this frequency is like probability, in order to estimate the density, we divide, forget about the sign of limit, we divide by the size of the interval. And we get the density. Now, why the density? I said it is interesting because if I want to compute the probability of the variable to be lower than 4, I can compute the integral of the density. The density, remember, was obtained by dividing the frequency by the length of the interval. The integral of the density is obtained by multiplying the density by the length of the interval, so I get back to the frequency. And the integral is a sum, so it's the sum of the frequencies. This interval is the sum of the frequencies. But given that each frequency was obtained by dividing the number of points into each interval by the total number, the sum of the frequencies must be 1. All the frequencies of all the possible variables. If I limit my attention between 0 and 4, of course, the sum of the frequencies, so the result of the integral, will not be 1 because I'm not covering the whole range, but will represent the probability of the variable to be lower than 4. And this is interesting for me as an engineer. This is what I want to obtain. So, moral of the story, the density is useful because if I compute the integral over the whole range of the variable, I get 1. If I compute the integral over an assigned range 0, 4, I get the probability of the variable not exceeding 4. Now, if this is true, we should be able to check it into our generation of R. So in R, what we did is to compute indeed the densities, because we counted the number of times the variable was included in each subinterval, and we divided this number of times by, I just want to remind you, we divided the number of times with this instruction here by 100, the total number of experiments, and by the size of the interval. So this vector B is indeed the vector of the densities. Let me plot it now. Let me plot it by putting on the horizontal axis the value of the variable. And this is what I get, okay? So if this, what I did is true, I can compute the overall integral of this function, and I should get 1. What is the integral? Is the area below the function. So if you look at this figure here, the area is, okay, the base is 8, and the average height is between 0.1 and 0.2. You understand, 8 times 0.1 is close to 1. So it is indeed something that looks reasonable that the integral is 1. But let me compute it, okay? So the vector of the frequencies is B, of the density, sorry. So if I want to compute the integral is sum B. The x is 0.5. It's 1. Now, if I want to get the probability of not exceedance of 0, let me check what is sum B, B lower than 0, times 0.5. I made some, sorry, it is not correct. Sum B, it's, let me check here. I think B1, 4. Only the first 4 elements, or let's say 8 elements, because B is long, is 16 numbers. You see, the length of B is 16 numbers. So if I get the sum of the first 8 is 0.45, which is the probability of the variable be lower than 0. Now, everything here is a bit, you see this figure is a bit rough because we did a simulation of only 100 elements. Let's see what happens if I make the simulation with 1 million. Okay, so let me go back. Let me go back to the simulation. Simulation is somewhere, let's see where it is. Here. So 1 million. Oops. 1 million. Okay, perfect. This is A. Now I have to repeat the 4 cycle. So let me get it. I think we can use the same discretization. So I think this is fine. Computation of B. Here I have to put 1 million. This is B, perfect. And then let me plot it. I think this is fine. Oh, you see that it's much better now. Still, the line is a bit but it's much better. And still, if I make the integral, it's 1. So we got to the definition of probability and probability density. One is the integral of the other, or one is the derivative of the other. So you can get the probability density by taking the derivative of the probability, and you can get the probability by taking the integral of the probability density. The probability density, we introduced it because we needed it for continuous variables. When you define a probability function, which I already introduced, it's a function that gives for any value of the variable its probability. You can specify either density or probability, because you can pass from the first to the second through integration. It doesn't matter. So now let's go here. Here there is a sketch which explains better how frequency is computed, but I think we can skip it. So this is an example of a probability distribution that is well known. It's the normal distribution. The normal distribution, or Gaussian distribution. Why it is important? It is important because it is useful to describe many random variables. You understand that each natural phenomena can be described by a probability distribution. If it is random, like wind forcing, like wave forcing, we can use a probability distribution to describe it. And the problem is to identify the correct one. So what is the best probability distribution for waves? What is the best probability distribution for wind? Each natural phenomena is characterized by a different probability distribution. And therefore, the literature elaborated several analytical expressions for probability distribution to be adapted to the phenomena that we want to describe. These probability distributions, these functions, typically are parametric. What does it mean, parametric? That they contain coefficient which you can tune in order to give some flexibility to the function. So one of these distributions is the Gaussian distribution, also called the normal distribution. You don't need to remember it. You see the formula here for the density. The formula is given for the density because you cannot integrate with an explicit relationship this relationship here that you see on the screen. So it is given in the form of the density. And as I said, you don't have to remember it. The nice thing is that if you look at the figure of this function for different value of the coefficient, which it includes, the coefficient are mi and sigma, you see that, or sigma square, it is because it's the standard deviation, it's the variance. But don't get trapped into the details, 2 coefficients. And for various values of the coefficients, you see here in the figure, different shapes, but they have one feature in common. The shape is symmetric. Is symmetric with respect to the parameter mi. Okay, and it is extended from -infinity to infinity, the range. So you understand that mi is a position parameter. You see that when mi is equal to 0, 0 is, you look at the horizontal axis, 0 is the axis of symmetry of the distribution. So mi is the position of the symmetric axis, axis of symmetry. Sigma is dictates the width of the distribution. If sigma is large, you have a bell that is very large. It's fat. If sigma is small, you get a bell that is small. You can recognize these patterns on the figure here. And you recognize also one thing, that given that the range is -infinity to infinity, it's not good for describing waves, because waves vary from 0 to infinity, but not minus infinity. It's a positive random variable. But still, this is a distribution that is extremely interesting because it allows to describe several natural phenomena. Okay. I think with Professor Archetti, you probably have already dealt with the Gambit distribution to estimate extreme wave height. It's a different distribution. It's maybe also simpler to use with respect to the Gaussian. The Gambit distribution is used to describe the extremes. By the way, into R, when I generated numbers with R norm is generation of random numbers from the normal distribution. And what I did as values is number of generations, me, 0, sigma, 1. If you compute the mean value of this mean, of this distribution, let's take 1,000 generations, the mean value of generation from the normal distribution. What is the mean? It's 0. So you understand that me is the mean of the distribution. And what if we compute the standard deviation? You know what the standard deviation is. It's a measure of variability. What is the standard deviation of this distribution, of this generation of random number? Is 1. So you understand that sigma, the second parameter, is standard deviation. Okay, I think I annoyed you too long already with probability. I think we can stop here. What I hope is that now you remember what is probability, what is probability density, and you remember that by integrating probability density, you get probability, and as such, by the definition of probability, if you integrate probability density over the whole range of the variable, you get 1. Because it's like considering all the outcomes from the space that you mentioned. Were you already, or are you already familiar with concepts of probability theory?
We had the first year bachelor.
Sorry?
We had the probability course first year bachelor in Bologna.
And did you have, in your case, some introduction in the Bachelor of Probability? Because you didn't take the Bachelor in Bologna, or yes? No. So you already knew something of probability?
Yes, the concept.
The concept, okay. You too, probability is known to you? Okay, okay, very good. But Professor Archetti already introduced how to estimate the extreme wave height.
We did last semester.
Last semester, so Gambit distribution,
Yeah.
correct? Okay.
Probably don't see that.
Okay. And, you know, actually, you may apply also this because the probability distribution, once that you introduce the probability, I mean, let me just, you can also use it, I mean, to estimate the design wave without knowing anything. But I think that, you know, if you don't know, or if you don't remember well what probability is, in any situation that you use a model without understanding the theory, I think it is potentially risky. But in any case, basically the probability distribution, let's talk about probability, not probability density, Px, allows you, if you specify the probability, Px is equal to Fx, okay? You can also estimate x as the inverse function of probability. And this is actually our problem. Our problem is that we have a probability that is given by legislation. So we are told that we have to design the Harbour by using wave height, which occurs with probability of 1/100. And then by inverting the probability function, we get the design variable sign. Actually, very often, the legislation doesn't give us probability. The legislation gives us the return period, typically in years. So they say wave height with the yeah, I think the range is placed here with d equal 100, which means you have to design for a wave height with a return period of 100 years. So given that they give the return period, you have to estimate you have to express t as a function of t. This is what you have to do. You have to make this transformation. And how to make the transformation? First of all, usually the legislation talks about annual maximum wave height, which means a random variable that occurs once every year. Sorry. Yeah, it's a random variable that you pick up once every year. So it's annual maximum wave height. You get for every year of observation one number. So the time span between the subsequent experiments is 1 year. So if the variable is sampled with a time lapse of 1 year, time interval of 1 year, the relationship between probability and return period is very simple. It is this one. T is equal to t minus 1 divided by t. So this means that a return period of 100 years, if t equal 100, then you get probability equal to 0.99. And it's a probability of not exceedance, be careful. So I have not exceedance for almost all of the years, but one over a return period of 100 years. So it means that if I look at the wave for 100 years and I take every year the max, for 99 years, I have a wave height that is lower, and for only 1 year, I reach such wave height. And this is what the wave height with 100 years return period, because it was reached only once in 100 years. So this is the relationship you have to move forward. Now, how can we define the return period? This is important because based on what I said so far, you may be misled. Why? Because so far I defined the variable with 100-year return period, such as the one that in 100 years occurs only once. Okay. So I said, okay, let's suppose that I have a graph of wave height, okay, and let's suppose that this is 0 and this is 100 years. And then this is my graph, okay? And then I take the max, and I say, okay, this is t equal 100 years. This is what I said so far. Actually, you know, this is right for this observation period. But if I go forward and I get to 200, what may happen is that I have such a situation. And therefore, the same value was overtopped 3 times. So what is valid for 100 years may be not valid for the next 100 years. For instance, because I got climate change. So how can I define the return period in a consistent way to say that I am expecting that this value is reached once in 100 years. This is my expectation. It's not certainty, it's expectation. Probability is not certainty. It deals with uncertainty, it deals with expectations. So let's define the return period. Return period in a way that delivers the correct concept. It's the average time. Average, this is the key, average time between what? Between two consecutive events. That exceed or equal a given threshold. Average time between two consecutive events that exceeds or equal a given threshold. So if the threshold is a wave height of 4 meters, it means that if I get a wave height that is equal or above 4 meters, I am expecting that on average, the next one exceeding or equaling 4 meters will happen in 100 years, on average. It means that it may happen tomorrow. It means that it may happen after 1,000 years. It's on average. So you understand one thing, that if you want to define a wave height with 100-year return period and you want to define it on average, it means that you mean an observation period that at least is 100 years, but should be actually much more than that, much longer. Okay, at this stage, we can move to our, let me see, we have less than 1 hour, okay. At this stage, we can move to wind loads, to wave forces. And you see here, let me move forward a little bit, what we are talking about now. The design wave is estimated for a given return period, which is defined as the average time lapse between two consecutive events with wave height reaching or exceeding a given threshold. Please remember this definition. It is extremely important for engineers. We use the concept of return period also in earthquake engineering, in hydrology, in many fields. Okay. So how do we select this return period, which of course dictates the probability? And you understand one thing, the longer the return period, the more I have to oversize my design. If I want a berth resisting to an event with 1,000 years return period, the berth must be very solid, because 1,000 year return period is something really huge. So, I mean, it means that your infrastructure becomes more costly. It means that you cannot exaggerate with the return period. So basically one would say, the larger the return period, the safer I am, the happier I am. But the larger the return period, the more costly the infrastructure. So I'm not as happy actually, because I have to spend a lot of money and the environmental impact is huge. So we have to reach a compromise. We have to be safe, but on the other hand, we don't have to waste resources. And therefore, the idea is, let's look at the consequences of a failure. If the consequence of a failure is an economic damage, I can take the risk. If the consequence of a failure is loss of lives, then let's increase the return period. Is it clear? Okay, now we already knew the relationship, we already illustrated the relationship between probability and return period. Now, it is interesting to look at the next relationship. So the joint probability that a given wave height is not exceeded in n consecutive years is obtained by raising the previous relationship to the power of n. I want to explain better. What is probability? It is the probability that in one given year, I get the wave height that is used for the design. Okay, so when I say probability is 0.99, I said this is the probability that in a given year, I get a wave height lower than the design one. The probability, the complement one, is the probability of getting a wave height equaling or exceeding the design one. In 1 year, this probability are expressed in 1 year. The question may be, and in 2 years, what is the probability of getting this wave height in 2 years? In 2 years, I have to raise this probability to the power of 2. So it means that in 2 years, not exceedance is raised to the power of 2, and exceedance, exceedance is equal to 1 minus 0.99 to the power of 2. So not exceedance goes down a little bit, of course, because I'm looking not at a single year, but 2 years. Okay, so it is interesting then to wonder, what is the probability of, in 100 years, to get a wave height with a return period of 100 years? So what is, if I look at the return period of 100 years, in 100 years, what is the probability of getting this wave height? It's not 1, of course. It's 63%, and this graph tells you that. So the lifetime of the structure is what I expect for the lifetime of the structure, and the return period is on the vertical axis. So my question is, if I have a lifetime of the structure of 50 years, and I take a design wave of 100 years, in 50 years, what is the probability of reaching the design wave? Okay, so I get 50. I go to 100 years, okay, and I see what is the probability is a little bit above 50, a little bit below 50%. If I get 50 years, 100 years, the blue lines indicate isoprobabilities. So the probability is a bit larger than, lower than 50%. If I take the same lifetime as the return period, as you see, I am sitting over the 63% probability blue line. So in a lifetime corresponding to the return period, I have 63% probability of reaching the design wave height. This is interesting. So, I mean, if you design for 100-year return period, you are not really safe. In 100 years, you have a probability quite relevant, 63% of getting it. So the consequences of your design must be duly evaluated. And this is written here. By looking at figure 8, one can see that a pore structure that is required to have a design lifetime of 50 years should be designed for a retro period of about 500 years if the probability of exceedance of the design wave during the whole retro period is set to 10%. So if I want to limit the chance during the lifetime to 10% of getting a given design wave, then for a lifetime of 50 years, I go up to 10%, it's here. The return period should be 500. This is a kind of reasoning that you will not see frequently. Reasoning based on the probability of getting a given forcing during the lifetime. Usually the legislation gives you the retro period and that's it. But you may find cases where the legislation says during the lifetime, I want a probability not above 10% of getting the design forcing. And then you have to use a graph like this. And here you read, similarly, by setting the return period equal to the design life, one can see that there is a 63% chance of exceeding the design wave height over the given lifetime. Okay, when you design berth structures, the usual return period suggested by legislation is 100 years. You may find different indications, especially if the risk is entailing loss of lives or very heavy consequences. And dams, to give you an example, you understand, dams are causing disasters if they fail. They are usually designed for a return period ranging from 500 to 1,000 years. Okay, now, what should we, what is the rule that we usually follow for birth? First of all, let me give you some rules of thumb derived from the Spanish standard, which I already mentioned to you. For the significant wave height, usually the design of birth is done with reference to the significant wave height. So it is computed in this way, the significant wave height. You take the recording of all waves, and then you take the upper 1/3 of the wave height, and then you compute the average. So what you do is you take the whole recording of wave height, okay, from 0 to, this is W wave height, to a certain extent. Let's say the max is W star, and then you take 1/3 of the upper max, and then you compute the mean value. This is a simplified way of computing the design wave, and it's called, as I said, the significant wave height. And in some cases, you may have, this is a kind of feature. The significant wave height is a kind of feature of the context, of the location. And of course, usually you get a recommendation to make the design with a given return period, okay? Or in some cases, you may get the recommendation to make the design with respect to the significant wave height, which means that you have to get observations and you can compute it in this way. So the Spanish standard says that the wave height, the significant wave height, which means the the design wave should follow these rules of thumb with pleasure craft, which means I mean small ships. The wave height for wave forcing, for computing the wave forcing, should be like 40 centimeters. For fishing vessels with the length overall less than 30 meters, 60 centimeters. For fishing vessels with a length of more than 30 meters, 1 meter of wave height. Other types of ship, 1 meter. And ship with displacement greater than 3,000 tons, 2 meters. These are the rules of thumb. And in order to compute the wave forces, take into account that usually these wave height are much lower of the design wave height in open sea. So this is a wave height that is considered not for designing ship stability, but just for computing the mooring forces. And we assume that the harbors are sheltered, are located in a quiet place. And therefore, these suggestions, you know, if you look at these wave heights, they are quite reduced. And keep in mind that if the situation becomes really bad, a ship can unmoor. So it is justified, the fact that the mooring forces are computed with wave heights that are reduced, because if you get to a limiting situation, you can unmoor the ship. The ship is designed to resist, even in open sea, to larger wave heights. Okay. Okay, so these are the limiting conditions, and these are the rules of thumb. Oh, sorry. And you also have the means now, if you are given a return period design, to compute your design wave. And now, basing on the design wave, you have to compute the wave forcing. Before we move to computation, let me just say one thing. Wave force, let me see. I think here there is a part that you can drop, which is related to wave breaking. And usually when we waves break when the sea depth becomes reduced, becomes small. Usually in harbors, you don't have this situation. But if you are asked also to design the depth of the harbor, you should take into account 2 things. First, the draught of the ships that you are planning to moor. So large ships means a larger, a deeper harbor. Second thing, you have to avoid into the harbor wave breaking, because you understand why. If the wave breaks, then there is also movement of mass. Besides the movement of energy, they have an impact over the ships. The situation becomes really a little bit risky. So we have to avoid wave breaking into harbors. And this is... usually, you know, if you have a break zone, it means that you have a reduced depth of the ocean. And this formula suggests, we will comment over it soon. So it is unlikely that you can allow such a reduced depth at the entrance of an harbor. Usually you have to keep a clearance that is really important. So usually waves don't break at the entrance of the harbor. But inside the harbor, if you get to some places where the depth of the ocean is small, you may get wave breaking. So it's important to avoid it. And in order to avoid it, you just have to keep the harbor sheltered and deep. And the depth, the limiting depth is dB. So if you keep a depth of the harbor that is larger than 1.28, the wave height, the expected wave height, so the wave height for a given return period, then they don't break. Yeah? Yeah.
If we want to design a harbor, do we know which kind of vessels are coming? Right?
Yeah.
How?
Yeah. It is derived from planning of sea traffic. So you may, first of all, you may have plans that are given by an authority. So if you get the commitment, the task by an authority, the authority knows because they have plan which are finalized to host a certain type of ship. So they may say, I want an harbor for tourism, for touristic ships. And then you know the type of ship that is going to dock. Or they may say, I want a commercial cargo with a tonnage of 20 tons. Usually you are given this indication by the port authority or by other authorities at the national level. Okay. And it may be based over an existing knowledge of ship traffic or a plan, a future plan. Like, for instance, several harbors are updated in order to increase the size of the ships that are allowed to dock. So you know this plan, the expectation. It's like a design variable that you get. So the depth of the harbor must be determined accordingly, basing on the clearance that this ship need and basing on avoiding the wave breaking. I tell you, usually the priority is given to the clearance because unless you have a very small touristic harbor where you may get enough clearance for the ships to dock, but not enough depth to avoid breaking, but this is a very, very specific case for small harbors. Usually with huge harbors, you have to make sure that you have a clearance such that you don't get breaking. If you look at the harbors where you take the ships to go to the islands, where you can load cars, you never see waves breaking there because the depth of the ocean is not allowing that. The depth of the water. Waves break only when you get into shallow water. And you see here the rule. If you have a wave incoming with an height, which means from through to crest of HB, let's say 4 meters, you need a depth of 5 meters in order to avoid breaking. And, you know, with the huge ships, you get a clearance in most of the cases of 15, 20 meters. So you don't have to deal with breaking. But of course, this is another parameter that you have to consider for designing the depth. Okay, let me just see if I forgot something. So let me just go back a little bit and let me see. We got here, we know this was discussed, vessel rotation, we discussed it. Okay, wave forces. Yeah, this box is just a curiosity. And you may have heard recently of anomalous waves. So there was a cargo bringing cars and trucks in an island. I think it was, I don't remember if it was Ischia last week. And they got an anomalous wave and the trucks went over the cars. So it was a trouble. And these waves, anomalous waves, or also called here rogue waves, monster waves, they are originated with phenomena of nonlinear interaction between waves. These phenomena are not completely understood. So it may happen sometimes that in an ocean that you have significant wave motion, but not really alarming, you get a single wave that is much larger than the other ones. And often it results from the composition of several trains of waves, nonlinear composition. And it is really a phenomenon that is concerning because it may cause risk also for very large ships. And if you want it's a curiosity, not for your exam, but if you want to know some more, and there is a Wikipedia page, and there are some pictures here. Freak wave, monster waves, episodic waves, killer waves are unusually large, unpredictable, and suddenly appearing surface waves that can be extremely dangerous to ship and isolated structures like lighthouses. And they are distinct from tsunamis. Tsunamis are caused by an earthquake. These waves are generated by nonlinear interactions. And I want to see, I think there are some figures here. Here you see a graph with this spike. It's unbelievable, it's a single wave. And this is in meters. So on average, waves with 5 meters high, then we got one of 20. And I'm looking for pictures. This is an experiment made in the lab, I think, or it's a simulation probably, because they are also trying to simulate with models. And
engineers do not consider it in designing, right?
No, we don't consider that because they are really, this was generated in the lab. Let's see, it's 40 seconds. You see the ship in there, and this is, for now, it's regular. But I guess at a certain time, we will get a larger one. Yeah, this is the larger one. It's nice. You find it on Wikipedia. As I said, just a curiosity. And let me just see. I think there is another link here, if I will remember. Here. No, it's not here. It's not here. Okay. Now, it would be time to get into the computation of the wave forces, which is not really, it's another empirical formula, but I prefer to postpone to next week and dedicate 20 minutes to reading the exercise, introducing it. And let's see, there is a video here. There is this is not really, okay, it's YouTube, so shouldn't be nothing compromising, okay. This is a simulation experiment in the Deltares lab. Deltares, they have a lab facility for simulating waves and sediment transport in harbor basins. It's very huge. It's a huge pool, and they make experiment with numerical models and small scale models. It's really interesting, and I want to show you, because this is a simulation, but I want to show you this facility they have in the lab. It's a small scale reproduction of wave motion and the pressure exerted by wave motion on the beach. And they can generate really large waves with this machinery. I went to see in person once. It's impressive because they can generate very large waves. And you see the size of the channel. It's compared to the humans, it's really a huge one.
I didn't put the glass there.
Sorry?
I think I put the beginning a glass on the right, on the left.
Here, probably because they want to see if the wave reaches that level. I'm not sure. I'm not sure. Let's see. Let's move forward and see what happens. I think more or less. I think I have. I think this is again delta Rs. I think it is the same experiment. Unfortunately, it's not possible to see the full extension of the channel here. Let me see. Because when you have these processes that are highly 3D, there is a lot of turbulence. So there is variability in the 3 dimensions. Numerical modeling is approximated. This one is nice. I think here we can see the full extension of the channel. Look, this is a real wave. It is impressive. You know, breaking. Yeah, I went once. I was in the public, like more or less here. I was on this side here, I think. Okay. Now let's go back to the exercise. And my suggestion is let's read it carefully. So a ship with a displacement of a tonnage of 3,350 tons, a waterline length of 117 meters, a draft of 5 meters, a beam of 12 meters, pivot point located at 55 meters from stern, and side projected wind area of 950 square meters, is moored to a berth with 6 mooring lines displaced as in figure 1, red lines. The yellow lines are additional ones that are shown for the sake of illustrating further possibilities. So we are considering only the red ones here. Actually, this is a ship that, to be safe, would be moored with the red plus yellow. But I removed the yellow lines because otherwise it becomes too complicated. Too complicated operationally. Conceptually, it's not more complicated, but okay. The ship is subjected to an extreme wind velocity of 50 knots, which means 92.6 kilometers per hour, with wind direction perpendicular to the ship center line. So it's transverse wind direction. The ship is moored with mooring lines composed by 3 ropes of cross-sectional area of 30 square centimeters each, because these ropes are usually made up by intertwining more smaller ropes. I don't know how to say in English, but I think you understand what I mean. It's not a unique body of rope. It's just different bodies. In this case, 3 ropes of 30 square centimeter each that are put together. The elastic modulus of each rope is 125 kilonewton per square centimeter, and the breaking tension is 25 kilonewton for square centimeter. So first we have to compute the wind force and the yaw moment. Yaw moment because we know the pivot point and let me see, and the ship side area, we will see what is the position of the center of gravity of the wind edge area. And then we have to compute mooring forces and safety factor for mooring lines by assuming that the ship is moored with the 6 mooring lines that are depicted in red. By assuming, again, that the origin of the axis is placed over the pivot point and assigning the following values to bollards and chocks coordinates. Okay, So we assume that the mooring lines are horizontal, which is not the case actually. And you understand, if they are inclined at an angle, meaning in the vertical direction, if they are inclined in the vertical direction, they have a forcing that is larger. If they are horizontal, is the best solution. If the mooring line is close to vertical, then the forcing on each mooring line is much larger. And then we assume CW equal 1.3, and the mooring lines are 15% longer from bits to bollard than the distance between bollards and chocks. Okay, so this is a box on displacement of mooring lines. Ever read? It's not part of the exercise, and it is interesting because you understand that around the positioning of the mooring lines, their direction, their combination, there is a lot of experience and thinking behind, and a lot of also of physical consideration and consideration of structural mechanics. Now, a solution. There is a R code for computation, and let's forget about it for now. Computation of wind force. Let's take a coordinate system on the horizontal plane such that the y-axis, the x-axis is the same as the ship center line, while the y-axis is centered on the ship pivot point. Okay, so it's here. Okay, good. Computation of the wind force, it's given here. So let's do it. Let's do that. Okay, and let's do that into R. We may make it also in Excel, but actually in R, I think it's much better. And I would say, I hope you installed the RStudio. Let's open RStudio. I don't have RStudio here, so I have to make a connection with, just 1 second, give me 1 second, because I need to share the screen, and then I have to make a connection with my PC in the office, because here I can't. So let's remote. Yeah. One second. Okay. Okay. Let's see if it works. Yeah. Yeah, it works. RStudio. Here. RStudio. Okay. I think we never worked with RStudio before. Do you have already tried RStudio? No. Okay, good. No, it's fine. So let me just. What is RStudio? It's an interface for R. You see here the R console. So the R console, it's just a second, because I wanted to share the screen again. Okay. Okay, perfect. Now, here you see the R console. So the R console works as we know. Control L, you clear the screen, no problem at all. What is the advantage here? The advantage is that you have other 3 windows beside the console that you can customize. For instance, here there is a window showing the variable that I already defined. So let's forget about them. It's they are already in my PC. But anyway, here you can find a list. So if you define a vector, A equals C, 1, 2, 3, you see that A appeared in the right in the window, and so you can have a overall view. And then there is another window which is now dedicated to plots. So if I make plot A, you get the plot in the window here, which is it helps in order to manage, together R, plot, etc. And what about the other window here? This is a script window, which means that sometimes into R, you may want to write the instructions into a script rather than directly in the console. What is the advantage of having a script? The script is a file that you can save, and you can save the instructions in a folder, in a file, to keep them for the next time. It's true that R has an history, etc., but it's also true that if you want to move to another PC and you want to repeat something that you have done, the script is like a code. It's useful. So instead of writing here A equal the vector 1, 2, 3, I could have written it here. And the difference is that when you are in the script, first of all, it's advisable that you save it. So you can save the script wherever, in whatever folder. And when you are in the script is not executed. If you want to run the script, you have to click on run. You see that in the console, I got the instruction of the script. Another way could be by clicking on source. And source means that it runs the whole script. Okay, so for instance, if I write here something like A times 2, and then I write here C equal 4, A times 2, if I click on run, it runs only the instruction A times 2. So if I click on source, everything is run. And in fact, here if you write C, you get 4. So it's better if you work with the RStudio, because you can decide whether you want to work directly on the console or over a script. And the script is something that you can save. This is particularly nice if you have a script that is already written. So like in my case, 1 second. In my case, I need to, let me see. I need to get rid of this and I think Control H, no. One second. Okay. Okay, I got it. In my case, I have the script here, output. So if you click here, this is the code for solving the exercise, which is not particularly long. And in this code, you see, I define the coordinates of the chalk, of the bollards and the chalks. Okay. So if I want, I can use this script entirely. I copy it, copy, and then I go into my RStudio. I'm not sure whether I can paste here. Let's see. Yeah. And everything is there. And if I make source, everything is already done. Sorry, like? Yeah, it is a function of R, this one. And, oh, sorry, I understand your meaning. Yeah, it's like writing a function, yeah. And we can execute one instruction at a time. So here, run, and I defined the coordinates. So CB, you see, oh, sorry, because yeah, you have to be careful of where you are typing. CB, I have the coordinates defined into a matrix. And look at the instruction here, what I did. It is an instruction called cbind, which means column bind, which means that these two vectors, the coordinates x coordinates and the y coordinates, are put together into a matrix, which is the one that you see here. Okay, now let's run this one. And then we have defined the coordinates of both of them, chocks and bollards. Now, in order to make the exercise, the solution that is suggested here is to write a function. We didn't talk about writing function in R, so we have 5 minutes. I propose to dedicate these 5 minutes to writing a function. Let's forget the exercise for the next time, okay? And the next time we will write the function that solves the exercise. But let me write a function, just a very simple one, in order to illustrate to you how functions in R can be written. So what is the purpose of writing a function? A function is, for instance, let me work on the console, square root. Square root of 4, it's a function that takes the argument between round parentheses and makes the computation. Why the function square root was created? I could have written 4 to the power of 0.5. But it was written the function because it's more handy if you want to compute the square root. It's more, it allows you to go to target in a quicker way. So what if I want to write a function which takes the sum of two numbers? Very easy. I need a name for the function, so it can be trial function is equal to, and then I need to write function. I'm writing on the script, function, and let's write now the argument AB, the two numbers to sum. Then I need a curly bracket. Okay, and then let's write inside the function what we want to do. So it is C equal A plus B. And then let's print on the screen, cut C till equal true. That's it, okay? And then let's source it, everything. Okay, now let's write trial 2, 3, 5. Okay, very simple. And now I want to write a default, A equal 2, B equal 3. I source it, and then I can make trial. Oops, sorry. Trial. Without arguments, 5. If I want to change the argument, I can make A equal 10. And you get 13. This is an easy way to create functions. Of course, in this case, it's not very useful, but if you have a long computation, indeed, it is useful. Okay. Any question?